Good morning, good day to everyone who are waiting for listening to listen to Dr. Professor Lajos talk. Um, it's my pleasure to introduce all of you to this Advanced Air Mobility webinar series. And today's talk is very special. The topic is space, air, ground integrated networking from single to multi-component. He's an eminent professor in mobile communications, and his record of accomplishment is extraordinary. I'll take 2 minutes to share some of the highlights. He received his PhD degree in 1983 from Technical University of Budapest, honorary doctorates from multiple universities, including the University of Edinburgh in 2015. And to my knowledge, there are very few people who had who built such a distinguished record of academic excellence. And we are fortunate to have him today. Now I want to take another few minutes. He's a member of Hungarian Academy of Sciences. He has served in various capacities, including editor-in-chief of IEEE Press. He has served several times as governor of both IEEE ComSoc and IEEE VTS. He's published thousands of research articles, tens of books, and helped so many young professionals. And he produced, or he supported rather, over 125 PhD students. And many of them they have their own distinguished records too, like professors in various academic institutions. And he's recently has been IEEE Life Fellow. He has been IEEE Fellow for a long time, but he's IEEE Life Fellow. There is an interesting formula, those who want to know how it works. He is also a fellow of Royal Academy of Engineering, IET, and EuroSIP. He holds Eric Summerfield Award. And most important of all this, he is a very simple, excellent human being. And many of us who know him personally, you know that he's one of an accomplished person. At the same time, very friendly and supports everyone, young to experienced. Thank you, Professor Lajos, for accepting our invitation to join us and give this talk. Please take over.
Well, thank you so much, Kamesh. When I stop blushing after this generous introduction, my hope is really to entertain this community, also inform, but predominantly entertain, because we have to be switched on in order to be motivated and inspired in our research. And so I will therefore keep the presentation relatively top level, so that you see the main research thrust, and you will find the related papers and the background reading, etc., as we go along, also cited. I also wanted to thank the team here back at Southampton, and quite a few of them are named here because I learned a lot from them. But you would find a lot of related papers at our website. Indeed, all of those that I allude to or refer to will be really at the website. So also sincere thanks to VTS. And if you are not a member, please join VTS, the Vehicular Technology Society. It's a vibrant, multidisciplinary society with a touch of a sort of application-oriented edge as well. And of course, the sponsors, etc. But we are a global society, so really, I'm sitting down here. You see this island, it's called the Isle of Wight, next to Southampton. And this is London, where I'm circling with the cursor so that you know where I'm sitting. And really, there's a lot of things about Southampton which you may or may not know about. One of the most interesting facts about Southampton is that this is the place where Marconi, for the first time ever, demonstrated the feasibility of radio transmissions. Now, this is not Marconi, this is my friend, Professor Savo Glisic, but he's over there at the other side of the Atlantic, where the signals transmitted by Marconi were received by these four huge antennas, which might look to you like a bit of a MIMO scheme, really. So you could argue that MIMOs are 100 years old or so. But this is still on just really telling you about Southampton. And the other interesting fact about Southampton is that this is where the Titanic set sail from on her really final maiden journey. And so you might have seen the film Titanic, and therefore you know a little bit about the city. And this is where Southampton Wireless is sitting now. And so you could say that Wireless started 100 years ago, over 100 years ago in Southampton with Marconi. We are at the top floor of this building, and below us is the famous Optical Research Center, which is uh, well known for the design of the erbium doped fiber amplifier, which is capable of amplifying light without actually going back to electronics. So that's their most famous invention. All right, so slightly more technically speaking, we are really at a crossroads today because we've been over the years optimizing wireless systems for single parameter sort of metrics, and many of them are well known, such as the bit error ratio, the distance from capacity, the throughput, all these sort of well understood metrics. But really, you cannot improve one of them without actually degrading several of them. And so this leads me to the very simple definition of Pareto optimality, which is a well-known branch in optimization theory. Today, we will be adopting a bit of a practical approach. So really, by definition, the optimum so-called non-dominated Pareto front is the collection of the operating points of a system where none of the metrics can be improved without degrading at least one of the others. So to make this really a bit more clear, what I mean by this is you can always increase the throughput, for example, if you can tolerate a higher bit error ratio. All you do is you switch from BPSK to QPSK and 16 QAM, etc. Keep increasing the number of bits per symbol, and you end up with a degraded bit error ratio. But this is just a trade-off, right? When we introduce, however, a little more related to Shannonian information theory, for example, we know that really we can only approach the capacity if we keep extending the channel coding block length. So that increases both the complexity as well as the delay. So my hope is that you really see the main thrust of why I feel that the time is ripe for really embarking on multi-component optimization. It's a challenge. It's a bit like really, you know, trying to solve a huge task step by step, because I mentioned the trade-offs to start with, and then we introduce maybe 3 components, 4 components, etc. It's a bit like the famous Swiss Army knife, that this is not the best pair of pliers in the world, but it actually works in many scenarios. And we know that the existing systems have a huge number of adaptive operating modes. So, a simple picture, again, portraying these trade-offs is to try and optimize the bandwidth, the bit error ratio, the delay, the power consumption, and complexity. And these issues were discussed in these tutorial and survey type papers down at the bottom, where machine learning and learning in general, including even quantum search algorithms, are extremely potent, powerful in terms of finding the non-dominated Pareto front. So deepening our discussions a little further, I already mentioned that the existing standard systems, starting really from the 3G systems and then moving on to the 4G and 5G systems, really have on the order of, talking about 5G, thousands of different operating modes where you can have something like 4,900 different interleaver and coding combinations, for example, so that you can maintain the target bit error ratio or the target performance of the system. And so to portray this in the popular spider diagram, you see here we have, for example, again, the same sort of parameters like in the previous slide, but talking about the spider diagram in a little more detail. So we have here the reliability, in other words, bit error ratio or symbol error ratio. You could also have, various other packet loss ratios and so on. Latency is clearly the delay, but not only the propagation delay, but also including the channel coding delay. Because even for the same coding rate, for the same channel code, if you increase the interleaver length, you are able to overbridge a larger number of fading events, and hence potentially average the bit error ratios. So as a benefit, you improve the performance, right? Purely the delay or latency, the code word length, the interleaver length. And then, of course, we could have, the data speed in megabits per second, and energy efficiency. I already alluded to that, but I'd like to go really very slow here at the beginning before I start galloping later on a little bit, so that we appreciate why multi-component optimization is so important. Of course, it's not unique to space and ground integrated networking or aeronautical ad hoc networks. The 6G systems will also aspire to achieve this. So you see here in the center, we have the IMT 2000, the Intelligent Mobile Terminal in the year 2000. And then as technology and science and research has improved, we were able to expand the scope of this spider diagram. And so the ambitious goal of next generation 6G type networks is really to improve potentially all of these parameters, but giving cognizance to the fact that whatever we do, we will have to tolerate that if one of the parameters is improved, this can only be done to the detriment of another one, or potentially several, right? So now I got to the outline, and I will elaborate in more detail in an aeronautical ad hoc networking context, simply because this is a less well documented area in wireless communications. And so these aeronautical ad hoc networks, the application scenarios, a little bit on the specifications, enabling techniques, and futures. So hope you feel inspired and motivated now. So we try and delve into the particular motivation behind the aeronautical talk networking now. So drilling down a little bit further in detailed research issues. So this is the map of the UK, and you see here that there are large areas, in particular the mountainous parts of the country, where there's really large coverage holes, because the roads are fairly well illuminated with radio waves. Simply, we create these, narrow, almost like pencil beam-like sausage cells along the roads. But there is nothing outside the roads in the rural areas, so the coverage is not very good if you move away from the roads. And the same is valid really for other countries. This is the United States. And again, you see these, the Midwest areas, etc., and large kind of rural agricultural regions where millions of tons of wheat come from, but it's only the old farmer chugging along on his harvester combine. So there is no teletraffic and there is no need for providing a high throughput in that area. Uh, but there are, of course, rescue scenarios, disaster scenarios, etc., where this is absolutely critical. And you see here, California, even there, the situation is similar to a degree, apart from the very densely populated areas. And when it comes to, say, for example, the wonderful subcontinent of India, uh, look at the large areas again. You know, the cities, densely populated areas, well covered, but there are large areas in this alluring country where radio coverage is not so good. And so we know that sort of wealth creation uh, typically depends on communications quite critically. And so the government is very keen on improving coverage in India. Satellites are, of course, one way of dealing with this problem. And low Earth orbit satellites have indeed progressed very much in recent years. And the third generation partnership project, namely the standardization body that really standardizes next to 6G systems, is actually looking into non-terrestrial networking or NTN networks. And the service they often refer to is direct-to-device communications. In other words, from satellite to the ground. Now, let's do a bit of mental arithmetics for a moment. So at 3 times 10 to the power 8 meters per second, what we have is the propagation delay for 300 meters would be 1 microsecond. So for 300 kilometers, if you have a low Earth orbit satellite up there, it would be 1 millisecond. So that's actually quite all right. It's shorter than the propagation delay of, say, the medium Earth or geostationary satellites. Indeed, the geostationary is inadequate for voice communications. And 36,000 kilometers from planet Earth, the propagation one-way delay is 120 milliseconds. So you can no way support lip synchronized video or multimedia, for example. Anyway, still on the motivation, how we sort of really avoid having coverage holes. And again, you look at Saudi Arabia, much of it is covered by sand. And again, a famous story actually that many years ago, almost 40 years ago, the British Prime Minister Margaret Thatcher uh, was really in a predicament, in a very difficult situation because his son was partaking in the Paris-Dakar car race and he disappeared in the Sahara Desert. So again, there was no way finding him during that era. So, you know, the rescue and disaster recovery, these kind of things are extremely critical applications. So this is the whole kind of global system now, the Space Air Ground Integrated or SAGIN system concept. And I alluded to the different layers of satellites. Later on, I will bring in a quantitative slide to talk about this in more detail. But from now on, I will talk a little more about how the commercial airliners can actually support the global communication system in terms of enhancing throughputs, or even if it's only tentative temporal coverage, but the coverage holes in unpopulated areas could be covered by these planes. Another interesting application I haven't actually touched upon as yet is Southampton is also the cruising capital of the UK. And so you see often 2 or 3 of these huge cruise ships carrying up to 6,000 passengers and they have a abysmally low bit rate to the satellite, which they have to share. So the teletraffic density on these ships is unbelievable. You know, reasonably well of people on um, potentially sort of holiday of their lifetime want to have access to the system. And this is the charging concept which we're talking about. So in terms of delay, of course, the high altitude platforms are even closer to the terrestrial systems. So, they would be up at 20,000 meters above where the passenger planes are traveling, which are typically at 10 kilometers. And so their delay is also very low. And a number of different high altitude platforms have been experimented with. Today, I won't be talking about these, although again, even tethered balloons have been proposed in various system concepts to support rural areas, for example. Now, this is an interesting high altitude platform, the solar charged UAV, which is essentially circling at 20,000 meters. And as you see, the wings are covered by solar cells, so they are capable of providing radio coverage. They can be also maneuvered to areas of sort of temporarily high teletraffic demand, like public rallies or like the Olympic Games and so on. All right, so I now move on to talk about the public airlines, and this is three interesting scenarios to consider. The left-hand side one is at London's Heathrow Airport, and the planes you can actually see. This was downloaded from FlightAware anyway, but there are several such servers where you can actually watch the planes coming and going. The middle one is the European scenario, and the right-hand side one is really portraying the transatlantic scenario. This is a 9 million square kilometer area, and it's got a large density of planes. So they could also provide radio coverage for the cruise ships, or in fact, any other ships traveling across the Atlantic Ocean. All right, so you could sort of really catch up on the missing details in this tutorial paper, which considers both enabling techniques as well as a variety of applications. But this is a global snapshot of where the planes are. It's quite interesting to see where the highest density of planes are. Of course, this is actually interestingly also where the highest teletraffic density would be. And the next slide indicates for you a global snapshot of the various ships. We have here the greens representing the cargo ships, and those are the most numerous ones here. Then we have the blue ones, just a few visible are the cruise ships, and then the red ones are the tankers. Again, lots of those, as you can see. And then we have fishing boats and so on. So if I just, anchor your eyes on this, go back for a moment to this one, and you can see that they are almost like each other's complements, but the planes would be very handy to harness in terms of really improving maritime communications. So how feasible is this? How many planes do we have up in the air? You might be reluctant to believe that this might be a feasible service, but at some stage there was a company which asked us to look into the feasibility of this. And so this example here is essentially the in-air transatlantic flights between London's Heathrow Airport and actually not just London Heathrow, but the top 5 European airports and the top 5 American airports. And so you see here that in the morning, let's see, the westbound flights are these red squares at the bottom, right? So these are going from Europe to the United States. And you see that around about 2 o'clock, it's peaking. The most planes sort of take off around 10, 12, etc. And the density is increasing up to 240 aircraft. When you look at the lilac colored one down here at the bottom, hopefully you can see my cursor, that's the eastbound flights coming from the United States to Europe. And so they quite nicely kind of complement each other. So the sum of the two, you see here these darker colors, undulate round about 200 or so planes. So if you divide the 9 million square kilometers of the transatlantic region by the 200 planes, you will see that there is a reasonable coverage during the most busy times in particular, but even during the less busy times, there's 160 or so going up to 280. Now, we played quite a lot with these numbers, and we created also various statistical models that can characterize the the planes coming and going, their departure times, and various other things. So you would find these papers, and indeed I will probably send a batch of papers to Kamesh and Katie or Kylie, who can distribute the related background reading. So let's talk a little more about the scenarios, okay? The golden colored item on the list. So taxiing is before taking off, then we have the en route, and then the holding pattern when the plane arrives at the destination, and then landing gradually, and taxiing and parking. So there's huge differences in terms of the propagation conditions. Amongst others, of course, the Doppler frequency, because taxiing is a bit like maybe 10 or 30 miles per an hour max. Taking off, we have here in the picture 25 to 150 meters per second. Bear in mind that meters per second must be multiplied by 3.6 to get to the kilometer per hour, right? So you can sort of see 1,000 kilometer per hour, which is the typical cruising speed of aircraft en route. We would have like 300 or so meters per second velocity. So it's quite substantial, and depending on the carrier frequency, you know, the Doppler frequency is extremely high. So in this context, there is now a lot of research, for example, on orthogonal time frequency space modulation, or OTFS for short, in order to mitigate the effects of Doppler, because it's more tolerant to Doppler than OFDM is, for example. This high Doppler in OFDM would result into extremely high intercarrier interference, so it would degrade the performance very, very substantially. Okay, so let's now look at the channel characteristics of these scenarios, right? So en route, arrival, taxiing, and parking. Fastest gradually slowing down. And so you can see here the en route scenario that really there's hardly any correlation versus time or versus frequency. So it's almost like an independently fading channel, right? And of course, you know, it's very hard to estimate such a rapidly fluctuating channel, because think about it this way, every time we double the Doppler frequency, in other words, the vehicular speed, these fades move closer to each other. The distance between them halves. So in order to maintain a certain target beta ratio, you have to double the pilot overhead. But if you double it and double it and double it at 1,000 kilometers per hour, turns out that actually non-coherent detection performs better than coherent detection, simply because the pilot overhead would be so excessive that we don't have enough pilots. You end up with almost literally just sending pilots in order to estimate the channel. So again, OTFS is a good countermeasure in this context, but I won't be talking about OTFS in great detail today. If you are a PhD student and looking for an exciting research topic, this is a hot physical layer enabling technique. It was only proposed back in 2017, and now there's about 1,500 papers. So it's just about the last moment when it's still worth actually delving into investigating OTFS. In particular, for example, it's multi-user performance, including coding for it and channel estimation and so on. Anyway, I have to sort of gallop a little bit now so that I cover all the slides I prepared for you. And this is the arrival scenario, so the other extreme, and observe that now the Doppler frequency is really fairly low. You are almost slowing down to stop at the gate, and so you could use easily coherent detection. So adaptivity, again, in this context is extremely important. Simple ways of using adaptivities, you could use the level crossing rate in order to determine what the Doppler frequency is and then switch between coherent, non-coherent transceivers. We've got some literature on this. By the way, feel free to drop me an email if any of this is of interest to you, and I can point you to appropriate reading. But many of you are, of course, seasoned professionals, and you're more interested probably in the design aspects of how to make money out of this, how to create profits and wealth creation. All right, so you see that the huge difference is taxiing and then finally the parking scenario. So there's hardly any fluctuation in the channel, and this is when everybody pulls out their phones, and suddenly, of course, the teletraffic explodes because everybody wants to announce to their beloved ones that they have arrived, or their business partners, etc. So the adaptivity in its simplest form, when I just consider adaptive OFDM, we could use the top illustration to characterize the channel quality. So the light color would indicate a high signal to noise ratio, and the dark color is when it's almost like an outage. So essentially, we're looking at this 3D diagram from above now, and characterized by the darkness of the gray shade as to how high the signal to noise ratio is. And you see here the adaptive allocation of the modulation modes to the different subcarriers. This is the subband index at the left-hand side. We have 16 subcarriers in each subband, and actually 32, apologies, because we have a total of 512 subcarriers. And down here at the horizontal axis, we have the transmission frame index. So agile adaptivity is very important. And this is now how a GPS-based adaptive MIMO OFDM system would perform as a function of the distance from the ground station, for example. So distance here is 10 to the power 4 meters is 10 kilometers, and 10 to the power 5 is 100 kilometers. So as we get farther and farther from the original departure airport, the throughput is decreasing. But of course, you could connect to the satellites, and so this way you would be able to have a more balanced performance. This is just a pure aeronautical ad hoc network performance in this slide. And so really another important number to bear in mind is that at 10-kilometer altitude, the radio horizon is about 700 kilometers. So you couldn't possibly transmit beyond this. Uh, and this is where you might have to again harness a satellite in order to provide you with something like a one-hop relay in order to cover uh, the whole potential coverage area. So let's now return to our original discussions on Pareto optimality. And in this context, of course, we can just be slightly theoretical. If you're writing a paper for the transaction information theory, you would even assume zero delays, and you would just be dealing with capacities and uh, the per channel use throughput, for example. But this is here the toolbox of adaptive modulation schemes in the current 3G, 4G, 5G transceivers, depending on what region you are in. You might be using OFDM. Indeed, OFDM was used in both the 4G and 5G systems. And that's another reason why OTFS is now being so vigorously researched, because there are certain weaknesses of OFDM which could be mitigated. Before that, in 3G, CDMA was the predominant technique. So outside shell here in this slide is really the set of different enabling techniques, including things like different coding schemes. You see here at the top, channel coding, convolutional turbo, LDPC, polar codes, BCH codes, etc. And in the middle, we have the kernel problems and the optimization problems. And so I'm really using this also to underline that very important fact that we really need Pareto optimization in order to progress our science. And I already briefly touched upon mentioning that machine learning is a very good tool in this context, and I will use well, I can't promise I won't use any equations, but I will use just one single simple equation in order to highlight how we could actually really implement Pareto optimization in our research. So here, a bit complex picture again, but on the left-hand side, you see the cost functions that we might like to use, the throughput, the bandwidth, the target signal to noise ratio, uh, then, down at the bottom, other kind of more secondary importance is assigned to the peak to average power ratio, the number of radio frequency chains, the overall, say cost function evaluations. We know that in general, maximum likelihood detection is excessively complex. All right, so at the right-hand side, we have the various techniques. And of course, in this context, the choice of the carrier frequency plays a very important role. So millimeter wave and terahertz frequencies, they tend to propagate almost like light, more line of sight. So their impulse response is typically quite sparse. And there's also line of sight blockage. So we know about the reflective intelligent surfaces, for example, which allow us to go in a zigzag shape, get around the different obstacles. Full duplex was a very hot research topic a little while ago, but now it's entering to a degree service. So there's less research on this. But, a lot of enabling techniques, like I mentioned, coding for OTFS is not clear what coding schemes perform best. We know that, for example, polar codes tend to offer slightly better performance for short block lengths than LDPC codes, and this is why they were picked for 5G for the control channel. Whereas LDPC codes work extremely well for high block lengths, but they give you a longer delay, right? So a million different instantiation of this Pareto optimality, the inherent trade-offs that we have to deal with. All right, so again, we could just spend an hour talking about this slide, and it would be fun. I am up for it when we meet up with some of you in the next conference. Like I guess Kamesh and I will go to VTC in Oslo. It would be really nice to have a focus session on this topic. You know, I would be very much up for it. But this is the one and only equation. As you see, it's actually a very simple one because my goal is to really inspire and, you know, you can follow up on the fine detail on the particular topic of your special interest. So the way we really carried out Pareto optimization, for example, for routing, was that we searched a large network. Let me just take a little step here first, and then I go back to the equation. So in its simplest form, here at the right-hand side, we have our uh, Sargent network, space and ground integrated network, including the satellites, the planes, and the ground stations, and so on. So I could create a little network here where there's a single hop from the ground, the source, up to a satellite and then down to the destination. So the propagation delay is relatively long, not atrociously long, but relatively long, like 1 millisecond, and then goes down again. But the distance is large, so we need a high power, right? So the delay is low, the power consumption is relatively high. Another alternative would be to actually use the planes in this picture at the right-hand side. So I could have a little zigzag from, say, I don't know, Southampton Airport to JFK in New York. And there would be many, many hops along the route between the planes and potentially even including satellites, of course. And so I could use a much lower transmit power, but the delay would be much higher because at every node, I would have to have a buffer and there would be a queue. So, you know, this is just highlighting again the associated trade-offs. And you could pick your own trade-offs. If you can handle multi-component optimization, you'd be so successful in terms of publishing in this area. So let me go back to this slide now and really just highlight in a little more detail as to how this Pareto optimization could be carried out. We could use what is called the epsilon optimization principle, for example. Suppose, the objective is to optimize routing to minimize the end-to-end delay, right? So it's a single component objective function, but I would set two constraints, subject to the constraints that the throughput is higher than, say, a minimum of, I don't know, 10 megabits per second, and also that the path lifetime, namely how long a path remains valid before it's broken up because the planes move so fast. And so the path lifetime should also remain relatively high because this is when we drop a call potentially when a plane moves out of coverage, for example. And so adaptivity could be introduced by gradually setting these epsilon values to relatively demanding levels so that no routes satisfy it in your simulations or in your analytical derivations. And then you could gradually reduce these epsilon values so that you end up with more and more Pareto optimal points appearing. But there will be always this trade-off that if you want to improve, for example, the throughput, then either the delay would have to yield or the path lifetime, right? So this is a three-component scenario. And indeed, I will demonstrate this in this little slide here for a particular scenario, a simulation we ran. So this is little Southampton's airport down. You remember the Isle of Wight, right, where Marconi worked? And there's this triangle, which is the satellite, and down here we are at JFK in New York. So the blue line indicates essentially a path which is probably the minimum delay path. You see here at the top left-hand corner, the blue line is the minimum delay path. Then we have two other options, design options here. Namely, we can have the maximum lifetime path because the planes follow each other like little ants across the Atlantic. So they depart and they travel at the same speed. So the link remains very stable for a very long time, possibly for hours as you cross the Atlantic. So this is the maximum lifetime path, but we also know that the delay would be relatively high for this path because there's many hops and many routing buffers and queuing buffers. And then finally, see these other little dots down here, which actually also indicate some of the ships. The ships could be used as relays. And so the maximum capacity path is the one where we have just very small distances across the whole network. So we need a very, very low transmit power, or we have an extremely high capacity because of the short distance, right? So I think you've got the point. We have here at the top, again, the throughput, the delay, and the path lifetime, a three-component objective function. And I don't think there's any literature on more than three components. So, this would be a word first if you could come up with solutions for this. And this slide, I'm almost done, but just to highlight very quickly here, there's three different matrix here at the left-hand side. At the bottom, we have the coverage ratio. In other words, what area of the network is covered. And you see that the top line here indicates a perfect coverage, well, near perfect coverage by the satellites, Starlink, right? Then we have here the dashed line is a pure AA net, an aeronautical ad hoc network. And this might remind you of the picture I showed you about the number of planes in the air. So you might think, so why do we need this if there's 100% coverage by the satellites? Well, for delay and throughput minimization, for example. So you see here, for example, the maximum capacity route here is the one here. The blue line indicates that we add together the throughput of the satellite, which was 20 megabits per second, and the throughput of the aeronautical ad hoc network. And so in the middle, we end up with improved performance. All right. So almost the last things to share with you. Here we have a simple two-component objective function, because you might be wondering how many Pareto optimum points do we have. So this is a different example. This is the BA289 flight from Istanbul to London's Gatwick Airport. And so for this flight, we had a large number of Pareto optimal points. On the left-hand side, we have the path lifetime, and on the horizontal axis, the path delay altogether. But if I add the third component, like we did previously, we have the throughput, the delay, and the path lifetime. So let's grab a couple of points from this interesting three-dimensional picture, where we have at the left, I'm moving my cursor along the delay axis, the throughput axis at the bottom, and then the path lifetime axis, which is the vertical axis. So if I grab this point at the top right corner, for example, then you would see that we can get something like a 20 megabits per second throughput. The delay would be like maybe sort of 60 to 80 millisec, and the path lifetime would be something like 40 minutes. So you can sort of spend time looking at this, and the picture is from this journal paper at the bottom, but we have a very light-hearted uh, magazine version actually, which is this one here. So this picture is from that magazine paper, and you could study this at your own pace. So this is really the end of our journey. I started out with a map. For every journey, we need a map, right? And I haven't even touched upon so many things today, but
If you
research is
get a chance,
ongoing. And
go to
I just,
YouTube and go Oscar's Wicket Opening. OMG.
Okay.
what was that, Kamesh?
That was somebody, keeping their
Okay, okay. Anyway, as I said, there's a lot of open problems in this exciting research area. Kamesh and his team is also working vigorously along these lines, although from different perspectives. And he's got a whole community, a committee under the VTS umbrella. So thank you so much for joining in. I much appreciated your company, and my hope is to continue the dialogue via email and at conferences. I'll be at VTC in Oslo in June, and also at WCNC in Milan at the end of this month. So let's see whether there's any questions. I spotted that there were some issues in the chat box, but I haven't had a chance to look at them.
Yeah, in fact, I will look at the chat. There were some questions which are more administrative, Lanza. But we have room for one or two questions. And if nobody takes that opportunity, and I will ask the question, but I will wait for others to, you can unmute your microphone and ask a question. Or you can just type it on the chat. Actually, in the meantime, while I'm waiting for others. First of all, wonderful talk, Professor Hanzo. What I feel is the topic is so timely. The integrated space, air, and ground networking is pursued by a lot of people, a lot of groups, and in all over the world. The second is it's so pleasing to listen to you, because normally when we give presentation, generally, less experienced people, we give talks on something that we did, but the way you presented is, I'm 100% sure that everyone, each of us, have something to take it and connect to, so they can go home and start working at, use these ideas to pursue their research. By the way,
I'm
this
so pleased if you found it
yeah,
inspirational. That was
it
really
is.
my main objectives. And if I spend time on very detailed equations, then might appeal to a tiny fraction of the audience. But today it was more on about really inspiring people. There's, by the way, a beautiful paper in the IEEE Communications and Service and Tutorials by Professor Nei Kato from
Okay.
Tohoku University. Very well cited paper, very readable, and so also highly recommended.
So for some of the problems, how do you get where do you get the data from? For example, the flight data, the optimization problem that you referred to at the end.
I'm so glad that you raised this. So, indeed, that is a problem, and we spent enormous amount of time in terms of generating data. And based on the data, we fitted mathematical models. And what we did, I didn't have time for this, but since you asked, I elaborate a little bit. So what we did was we had the data, for example, the departure time of aircraft. And then we tried to use a large number of different hypothesis distributions in order to characterize that data. And we fitted these hypothesis distributions, and we evaluated what is called the goodness of fit metric of these distributions. And it turns out that actually a Gaussian distribution is a reasonable approximation. There are other good approximations which are slightly better, but you could actually assume a Gaussian distribution for the departure times of the planes. And because they travel at pretty much the same speed, so you could actually predict where they are, and therefore you could actually create a network based on it. And we had a quantitative paper on this in the Transactions of Vehicle Technology, which we did with DLR from Germany. And that was looking at an Australian scenario, but the data is suitable also for the European or transatlantic and various other, potentially the Indian terrestrial scenario as well.
All right. Just one more question is, normally, when we go up in altitude, increase the altitude to the level of flights, most of the literature actually say, oh, can assume a free space path loss. But in your experience, did you see something like, at what heights, altitudes we can assume free space as opposed to the multi-paths and other scenarios? At what altitude do you think it is reasonable to assume free space?
Yes, all right. So talking about propagation, if you allow me, I will start with a slightly broader perspective, because we all realize that, the most important thing is to gather measured data and then fit propagation models. But it's extremely expensive to take up a plane and carry out propagation measurements. So the most recent one is about 20 years old now, and it was carried out by a gentleman called Eric Haas from Germany. And so we essentially used his propagation models. And indeed, the different type of models are used today, namely the taxiing, the parking, the en route and landing, were based on his models. So he's got a table which is a fairly reasonable table to use for different scenarios, which are very different in general. The other reason we involved DLR in this TVT paper I mentioned is because they did some recent measurements, but only partial measurements because it's so incredibly expensive. And so if you look at the existing systems, even the old-fashioned GSM system 40 plus years ago had the hilly terrain model, had the rural model, and had the urban model, and had an equalizer test pattern. So we had to really use at least a good variety of different propagation models in order to characterize the system adequately. But this requires a large, a whole army of the VTS membership and the Communication Society membership in order to make progress.
Thank you so much, Dr. Professor Lajos. So I don't see, there are some questions, but they're all small things that I could answer. I mean, they're not, they're more administrative questions. And once again, thank you for everyone who joined, and we can wrap up the presentation, Professor Hanzo. The recording and including the slides will be made available, and I put the link on the chat for you to access. Even the previous talks are also available. And yeah, with that, I would like to thank Professor Hanzo for giving a wonderful presentation. This is useful for young professors as well as experienced professors as well. Thank you for giving us this excellent talk, Professor Hanzo. Thank you.
Thank you so much for your warm reception and very pleasant moderation. So I wish you all a good day or good evening wherever you are, and see you soon. Bye.
Thank you.